with that, we'll actually go and start working on some a little bit more advanced topics. So we will start moving towards some real analysis, like going into regions of interest, how to create them, how to move them around, what we can do with them, what we can do post execution. And I think in that session we will already get to some 1D concentration profiles, because this will open up some time in the next session to get a little bit more creative with all kinds of generalized analysis, spatial analysis, and so on and so forth. But very often the basis of everything is actually having yes, the recording is started. So the basis of everything is actually having regions of interest and the like. So we'll do what we always did before. So we'll just load the isotope table, load the color scheme, which now of course doesn't contain the aluminium hydride and so on and so forth anymore. So I will just add those 3 atoms to the color scheme and open our aluminium EPOS data set. So pos equals pos to table, and it's an EPOS file that you all should have. Then we also open a mass spectral figure. Oh, it's still loading the EPOS file. Sorry, I was getting ahead of myself there for a second. Okay, so we've got the mass spectral figure, and I might actually keep that docked here so that we can always see what's here in the mass spectral figure. And obviously we'll go and allocate the ranges, and we'll work based on elements right now. It's very often in oh, sorry, my bad. Of course, I have to go and select the mass spectrum and load it in. Obviously, this would also work. Oh, no. Because I haven't... Obviously, because I haven't gotten the axis, but yeah. Now we've got the spectrum again. And we can work off of this mass spectrum. Again, the reason why we use not the axis for the mass spectrum, but the spectrum itself, is because you can and you will occasionally have 2 or more than 1 mass spectrum in there, and then we need to be specific which mass spectrum we work off of. Okay, so the next step is then of course to allocate the ranges. Yeah, we've done that many times before. And and now we will create a plot again, and in this case maybe we want to have a look at one of those nice little needles and do some 1D analysis, some radial analysis, whatever the hell we want to do. Anyway, we will start building up an analysis based on regions of interest. And with that, I'll also explain a little bit of the background of what the objects consist of and what you can do with them. Okay, so I will go and scatter plot post data, and not all of them, just the silicon. and I requested 1 million silicon atoms, so it just gave me a warning that I don't have 1 million silicon atoms, which is fine. We'll just have all of the silicon atoms. And now, of course, we have these needle shaped, which I think are S phase, probably, beta prime. Any aluminum experts? I think they're beta primes, right? Anyway, so what we could think of is just to have some kind of analysis of one of those needles. So we might be interested in how the composition goes along the needle, or how it's radially defined, and so on and so forth. And any one of you that has used that has used proximity histograms and isosurfaces before might be already pretty aware that that probably an isosurface is not going to be very helpful if you want to have a radial profile, because it's going to be very noisy at the surface. We'll get to isosurfaces a little bit later. Anyway, so what we want to have is we want to have some region of interest in there where we can pick one of those needles. And what we can do in this case is we can create a region of interest object, which I will just call ROI. Yeah. Obviously, you can call it Dave if you want. You can call it whatever you want. And they're all of our region of interest things start with something with ROI. And I will actually start with the simplest ROI, which is a box. We can also have cylinders, planes, spheres, and work coordinate systems, and we'll get to those in a second. But I'll go with a box for now. And the box will have dimensions, a location, and we will plot it in a specific axis. And so the dimensions that I want to have, and it doesn't really matter that much with what I start, because I will use a MATLAB app to move it somewhere and to change its size. But maybe at some point you want to programmatically create them, then obviously you want to be able to say, okay, I have 50 data sets and I want to have a 20 by 20 by 20 nanometer cube in each of those data sets, smack bang in the middle, then you might want to do that programmatically. But for now, I'll just do it 10 by 10 by 10 nanometers. The location is going to be just 0, 0, 0. So at the origin, and the axis is going to be, well, what is the axis going to be? I should have probably saved the axis. And I hope the current axis is still the one they were working in. Anyway, yes, it was the right axis. Otherwise, it might have plotted it into the mass spectrum, which is not what we want. Anyway, so now we have a cube sitting here, and that cube is not super helpful. Because it just sits somewhere up there in the corner and we can't do much with it. What we can see obviously here is that if we use a box, we can see the coordinate system of the box. So the coordinate system of the box starts in the corner, and that is important, okay? But what we can have is we have a manipulate a ROI manipulate app, which you can open, which doesn't have any inputs. And this ROI manipulate app allows us to, well, manipulate the ROI. And in order to be able to do that, we need to tell it which ROI. And I think I called it just ROI, did I? Yes, I did. And then I can go get object, and you will see, okay, now we have the size, the location, and we have some options here. So the options, they are very important. So wait, I'll just put just share that with you. And the options are very important, and we'll get to those in a second. So the ROI manipulation app actually allows you to move the ROI around in certain steps. So the rotation step is in degrees and the move step is in nanometers or units of whatever. You could use that obviously for not add-on probe data for something else as well. But the move step here is obviously nanometers. And we can move the box along its local x-axis. So x-axis means along the local x-axis. So if we tilt it, it will follow the red line and not the global red line. Yeah, it will follow the red line on the cube and not the global red line. And we can rotate it, and the rotate is like in the rotational angles are like in an airplane. Yeah, so roll means this way if you're in the airplane, pitch means this way, and yaw means this way. Yeah. And the reason why we're doing this is because if we go by Euler angles, you will have gimbal locks, which is really annoying if you want to align something. Yeah, and this is why we're going with local angles. And here it's 1 degree steps. And then here we have a field where we can put any MATLAB code that we want to execute after each move of the cube. And this will come in very, very handy. And I'll show you what you can do with that. And the two main things that we do with that is that if we, for example, do a concentration profile based on our region of interest, we can always recalculate it after each step. Yeah, this is one thing. And another thing that is very helpful is that if we, for example, want to see atomic planes in our atom probe data, and we want to have a region of interest that it's perfectly aligned with the atomic planes, then it's really cool that we can open up a second visualization. So we can open up a second scatter plot where we only display the atoms that are within the region of interest and align them with the region of interest. And so you can see that you can very, very finely then move around your region of interest and have it move around until it's perfectly aligned with the coordinate system until the planes are perfectly aligned with that. How is this related to Andrew Breen's and Vic's toolbox? I have no idea because I don't know Andrew's toolbox, and if Andrew has some cool code in that area, I want to see it. And actually, some of the code that we are using for region of interest here has already been taken up by Konstantinos Hatzoglu, who is at NTNU now. And he will show us his user interface later today. And what he has is very good spatial distribution maps code. So I think what I will do is I will steal some of Costa's code and use that so that he can also do that with spatial distribution maps. Okay, but for now, let's start and move the cube. So, well, it's pretty obvious that, first we might want to go to positive C. Obviously 5 nanometers is maybe a bit of a better step size. And so we can start moving our cube around. And we might want to pick one of those precipitates. Maybe, I like this one. Yeah. So I can go and move my cube there, roughly. Yeah, so I'm going for this one here. I don't know why, I just picked this one. Just move it here, and then I can go and start rotating my cube. And it will always rotate about my view axis. Okay, so if I change my view axis, it will rotate about the view axis. That's why I went and just started viewing the whole thing head on. stretch it up and maybe roll it a bit more. Okay, but now I think we are fairly nicely aligned. Obviously, in the length direction, we are not as nicely aligned. We still have, sorry, not the length of the cube that we would like to have. So we can go and make it maybe 50 nanometers long on the x-axis and move it in on the x-axis. Okay, so now we have the precipitate in our region of interest. And you know, it's not perfectly aligned, so we can still go and roll it a bit more and probably move it in along the x-axis a bit better. Maybe it's better if we look from the top a little bit. Yeah, I think that's already a pretty good case of visualizing just the data that's inside the cube. But you can see it's relatively easy to just create one of those regions of interest and move it where you want it to be. And now I will just create another one just to show you the different region of interest options. And the next one is, I will just call ROI2. And we'll make it a cylinder. And the cylinder has a radius. And the radius, let's make it 10. With a height of 100 nanometers, and the location is going to be 0, 0, 0 again, because we're going to do some manual alignment. In this case, we need to say how many segments we want to have, because it's not a cylinder in the sense of a cylinder with infinitely smooth cylinder shape, but it will have segments. And this is very important because it has big implications on the performance of the containment test. Yeah? So containment test means it's a test. It's for the way for us to find out what's inside the region of interest. And usually, 16 or 32 segments is a pretty good number, and we're using the current axis. And if I now go here, you can see we have our cylinder. So the difference between the cylinder and the box, the important one is that for the cylinder, we don't have those coordinate system lines here, but I can tell you that the cylinder coordinate axis goes down the middle, and not the corner. Here we've got the corner, here we've got the middle. And similarly, we can go ROI 3 equals ROI create sphere. For the sphere, we can have a radius, obviously, only. Let's make it 50 nanometer radius so we can see it well. And then we've got the same thing. It's actually made from triangles, and we need to say how fine we want the subdivisions of those triangles to be, and I'll just use one with subdivisions 2. You can look up Catmull-Clark subdivision surfaces to see what the subdivisions mean. And the location is going to be 0, 0, 0 again. Just put it there. And in the current axis. And now you can see we've got the sphere as well. And if I go on to the legend, you can see we've got, all of them are gray now, so we should probably go and change the color of that ROI. Maybe we'll change it to something greenish or something purplish. My color selections are always really bad. And then you can see which one is which. And I don't know why the cylinder doesn't have, why the sphere doesn't have a name. We should fix that. So note that there's a bug because the cylinder, the display name should be called that. And here the display name, we can just call it sphere ROI. Yeah, so now it's called sphere ROI. And so on and so forth. And this would, could, for example, be some kind of analysis setup. Obviously, in our case, we can just go and delete the cylinder and the sphere because we don't really need them. That's not what we're after. What we want is looking into this thing here. So the next thing that would interest us, obviously, is, and for the sphere, obviously, the coordinate system 0 is in the middle of the sphere. Right. And what interests us now in this case is how to visualize what's inside here, or generally how to get an idea of what's inside here. And for that, we need something that's called a containment test. Yeah? And a containment test is simply a program that tells you, based on some kind of object, whether something's inside the object or outside the object. And there's different ways of doing containment tests, and we have two containment tests that are important for you. And one is a so-called convex containment test, which means that essentially whatever object you want to use to say if something's inside or outside can only be convex. So just as a reminder, you know, this is an object that is only convex. Oh, maybe this bit here is not completely convex. Yeah. And this is an object that contains concavities. Yeah. So this is convex, and this part is, so this is convex, and this is concave. Yeah. And the big difference is that if we want to have, maybe I should also explain that on the tablet, is that if we want to have a containment test that works for concave objects, it's more complex than for convex objects. Because for convex objects, if we make the object up of, you know, individual segments, and this is always what we do in computer graphics, then all we need to do is essentially put a whole set of planes here and test for each point whether this point, so I can I can, for example, make a green target point here and a target point here, and see that if we know what the surface normals are for each of those planes, so the surface normals always pointing outwards in this case. What we can do is we can look up for every single one of those line segments whether each point is on all of the positive sides or on all of the negative sides. And if it's inside, then it's always on the negative side of those arrows of those surface normals. If we do that on a concave surface, then we need to actually have a much more complex test to do that. I'm not going to go into detail how to do that. Maybe I'll do that when we get to our convex test, because I've written one that's fast but not super accurate. But you can get some that are super accurate as well. But for the most parts, we don't usually have objects anyway where we need concave containment tests. If you want to use an isosurface to crop something, then you actually need a concave containment test. So how do we do that? We can do that by just creating a logical variable. Okay, now obviously this has been renamed. Can one of the tutors help me what the containment test is called in the... oh, thank you. Pos in convex hull. And so we need the pos file. We need, and then we actually don't need everything from the ROI object. All we need is the corner points of the ROI object. So the corner points of the ROI objects are then ROI dot vertices. Okay? Vertices are points making up a graphics object. And then our containment test will run. And I'll just show you the options. So the options you have here is that you can also provide a tessellation, which is not important, and a tolerance. Yeah? So that if you have points that are sort of very close on a boundary, that you can also take into account that they have some tolerance to be inside or outside. But we are not going to use it very much. So almost all of what we need is essentially just the pos file or the pos variable and the ROIs vertices. And then you can see that we have a logical variable. We haven't had logical variables so far, but all of what the logical variable does is having a 0 where an atom is not inside and having a 1 where an atom is inside, or a true and a false, however you want to call that. And we can have a quick look how many atoms are inside by just typing number of non-zero elements. So NNZ stands for number of non-zero elements of in. And we see that it's 127,000 atoms roughly that's inside of our region of interest. And if I just want to display anything that's in the region of interest, I can do that. So I can, for example, go and make a scatter plot of pos in and just use silicon. And in this case, we just use all of the atoms. And then we get a plot where we only have this one thing that's in there. Yeah. One thing you can see already in this case is that obviously we're still in the same global coordinates that we were before. So if I compare that with our thing here, then you can see that we are roughly still at 100 nanometers Z. So we're still in the global coordinate system. All we've done is taken everything that's in the region of interest. We haven't done any coordinate transform or anything to the region of interest. And this is obviously the next thing we're going to do. So can any one of the tutors remind me what the coordinate system transform is called now? Maybe I could just open the MATLAB live script for that. Cylinder, row, sphere, cropping, manipulating, transformation. It's just called coordinate system transform. Okay. Okay, so we I'll just call it pos ROI Um, and I think the points are going to be pos in dot x, and don't worry, I'll copy that for you. Y and Z. Oh, and our ROI object is obviously called ROI and not ROI object. And now you can see we have the transformed coordinates here. So if I want to transform that in our POS ROI, then I can just use the X, Y, and Z coordinates here. And there's probably... Okay. So if we want to use that for display, then we can just go what did I call it? The POS. Oh no, I called that POS ROI. POS ROI transformed equals POS in okay, and now we've got all of the ones that are in there, and POS ROI transformed dot x equals, I should have called the POS the other one different. I shouldn't have called that POS ROI, I should have called that coordinates transformed, something like that. Coordinate transformed, and then we can go POS ROI transform dot x equals chord transforms the first ones, and we can copy and paste that 2 times over for Y being the second one and Z being the third one. And now if I do a scatter plot, then I can do that with POS ROI transformed and the silicon, and now you can see this is all properly aligned, and you can see that there's probably some room for improvement. And let me just copy all of that for you so that you can do that as well. And don't be afraid of that amount of code. Now we're actually getting to points where we use more and more code to make it more and more reusable. Of course, we could write a little program that, you know, where you put in the POS file and it gives you out a POS file. But if you want to use that for other things other than atom probe, then it gets confusing for people. And I think this is not all too complicated. Yeah, but I think what we have now is just a very nicely aligned region of interest. But I've promised you that the nicer things, one of the nicer things we can do is actually do a display that updates with us updating the with us updating or with us moving the region of interest. And the way we do that is actually that we can go and assign to that scatter plot here. Did I create the, yeah, we have gotten the scatter plot. We assign that to a variable. So we can call that silicon plot. It is that object that we have just selected. This is our silicon plot. And what we want to do is that every time we move our region of interest using the ROI manipulate app, we want this also to update in the silicon map here. So what we are going to do is we are going to go and assign those updated coordinates to that scatter plot. So that scatter plot does have X data, Y data, and Z data. And we can override that with the updated coordinates. Okay? And so what we are going to do is we are going to take some of that code from here. Okay, yes, this actually might require some kind of mapping toolbox because of the coordinate transform systems that we use. So can I get a raised hand from everyone that does not have that toolbox? Okay. I have to admit I was a little bit lazy when I programmed the coordinate transform because I used a MATLAB function that is part of a toolbox, and I have to remember which toolbox it is. But apparently there's a number of people that do not have that toolbox. So what I will do is actually change it and use a transformation matrix where I have to program the transformation matrix. That's not a whole lot of work, but it's just something, something that I was sneaking around doing. It's always good to be able to do rotational matrices and matrix transforms for coordinate systems anyway. So I guess that's something that I then need to put up on my list of things to do. Okay. So what we want then is to take that coordinate coordinate system transform. I think the coordinate system transform itself is that function. I don't think that's a function that we are using, that we have programmed, but it's something that's not super complicated to program. Anyway, so we will put this into here, and I might just make that a little bit wider here so that the whole line fits into here. And so we still do the indexing and the coordinate transform. And now what I'm going to do is that for our silicon plot dot x data, say that this is a coordinate transformed all of the first entries, and do that accordingly for the y and the C data. And now I will just make this a little bit smaller, because now we're mostly going to be looking at this figure here. And now if I start okay, now where did I move it? Oh, now I took all of the atoms, not just the silicon atoms. That is my bad. So coordinates is pos in. So sorry, my bad. We obviously also need to make sure that it's only the silicon atoms. And don't worry that the code is getting longer. I will always copy that for you. And now I should be able to only see the silicon atoms. Yes. So next thing I want to do is to go into XY view, and maybe, you know, we need to go into the positive X direction a little bit, maybe with 1 nanometer steps. No, that's the Y direction. Oh, that was the wrong direction. And now we're pretty much smack bang in the middle, so you can see 0 is now right here. And I want to go and look from the top and get the rotation maybe a little bit better. Yeah, it is looking pretty good already. Next thing is probably we want to move along the Z direction a little bit so that we can get stuff a little bit more in the middle here as well. Probably in the positive direction. We will make a move step of 2 nanometers so that you can see a bit better what's happening. And I want to make it a little bit shorter, so it goes from here to here maybe, so maybe 30 nanometers or 40 nanometers or something like that. Oh, and now we have lost it a little bit in this direction, but that's not a big deal. We can go align it in oh, and one thing I've totally forgotten is that we actually should probably redo the convex hull test as well. So copy that. So now I've never changed which atoms we're actually working on, and I was wondering why the box doesn't move. Box doesn't move because we didn't do any of this. So we didn't rerun the containment test. Now it actually rerun the containment test. Okay, which means we probably should realign everything from the top as well. So obviously this is not, this always takes a little bit of time to execute. And one of the biggest reasons for that is that I'm using a data set with 20 million atoms, right? If you use a smaller data set, then it doesn't take as long as it does here. Oh, and I think I'm at the wrong direction. Yeah, I was going the wrong way. My bad. So if you do that on a significantly smaller data set, then everything executes much faster, obviously. And the containment tests are usually what takes the longest. So I think it's a pretty good idea if you're aligning something that you just make a comment out of the containment test. Then everything runs a whole lot faster. Yes, you can downsize. Yeah, if you do course alignments like that, Andy is absolutely right. You could just use 1% of the data, then it goes much faster as well. So if you do it with only 1% of the data, it will be pretty snappy. So the containment test is implemented as QHAL. So it's the convex containment test is implemented as QHAL. And I know there's more modern algorithms, but unfortunately I don't have them. The point is in convex polyhedron. This is correct. Yes. And I probably should have taken the downsampling approach. Then all of this is a whole lot snappier, which we have actually enough time to do that. So let's maybe just do that then. Well, one thing we can very easily do is just use the silicon atoms. Yeah. Because if we just use the silicon atoms, then there is not a lot of them. So we can use all of them. Yeah. We can still use all of them in a display here. But when we do the alignment of the box, we might just use just the silicon atoms. Is it possible to obtain the ROI as a Voronoi tessellation? I don't know what you mean by that. Because the ROI is a or what you want to do with the Voronoi tessellation. Because of course you can do a Voronoi tessellation based on the ROI, and we'll get to Voronoi tessellations and what they mean later on. But Voronoi tessellation is not. I mean, I use it in clustering analysis, but it's a very general concept. Voronoi tessellations are very general concept in geometry generally, and we will get to them in depth later on. But I think one thing that would make it very simple is just to have a silicon pos. So silicon pos being pos dot atom equals silicon and all entries thereof. And if we may, and this silicon atom, the silicon thing that only has, I don't know, 70,000 atoms or so, and this will calculate much faster, obviously. So what we can do then is go in is pos in convex hull using just the silicon pos. Silicon pos, then do a coordinate system transform. In this case, obviously, we can get rid of the indexing here because all of the atoms are silicon atoms by definition. But probably doesn't make much difference in terms of performance. So I'll just leave it in for now. And if I go now and move things, it will be a whole lot snappier than it was before. Matrix dimensions don't agree. Okay. Again, you're also working. You're also learning troubleshooting here. Silicon pos. So where do we have? Okay, this is a bit of a not very. Because this is now, of course, the containment. Oh, sorry. We obviously also need to do the coordinate system transform for the silicon pos. That was my bad. Still not happy? Oh, now I've deleted the command that makes it into a matrix. That is definitely an error. Okay, now you can see that we are transforming all of them. Oh, of course, because... But you can see now it's pretty snappy, right? Even with all of them, but we don't want all of them, so silicon pos.x is... We just want the ones that are inside. And now that's what we want, right? So now you can see if you don't have that many in there, then it becomes pretty snappy. And really only if you have data sets with a couple, with sort of more or less much beyond the million atom mark, then it becomes a problem. Oh, that was the wrong transform, so this is probably then pitching it. And now we have our little precipitate properly aligned. And I think you can all imagine that it's also relatively simple to do that with some sub-volume of the data set if you want to rotate it around. What do you mean by SVD? So Andy, don't be afraid to say something. Don't be afraid to switch on your microphone and talk to us.
It's signal value decomposition.
Okay. Yeah.
So you do a principal
component. Yeah.
Yeah. It's your like go-to fitting thing. If you've got like a oblate spheroid, you find the principal axis of it.
Yes. So a quick explanation what Andy is talking about. So. If you have an object in there, and in this case it's a rod, what you can do is you can essentially calculate its moments of inertia. So you get a matrix of moments of inertia, and you can do a principal component decomposition of those things. And what that would give you is it would tell you that you have three very distinct axes, and that one axis is essentially along the rod here. And you could use that as a sort of smart snap snap smart align function. It is actually a pretty good idea and not actually too complicated to implement. And it would work pretty well for anything that's sort of a rod shape or anything that's sort of like a grain boundary or flat shape. You could use that very simply to align that. If you have a very big data set and you still want to use the entire data set and you will still want to keep things snappy, one very simple way to do that is to produce some pre-cropping where you just crop by the x, y, and z coordinates, and then just do the convex hull test on everything that's still contained in those x, y, z limits. I'm not quite sure if I should show that to you now because that's a little bit of coding, but essentially it's a couple of lines saying just throw out everything that is below the lowest point of the ROI or be above the highest point of the ROI and below the x most and the x least point and so on and so forth. And this gives you some pre-clipping in the code, and it would also make things a whole lot faster. Yeah, I will actually just quickly code that later on and put that in the in any of the material that you get later on, so that you have that pre-clipping implemented as well. Okay, but now we have a region of interest, and we know how to coordinate transform into the region of interest. And based on that, we can do quite a lot of analysis. So this object now, by the way, exists independent of any plotted data, right? So you could use that either on those single things here, or on some other copper or whatever. I might just adjust the pitch a little bit because it's not quite perfect, but I think now we're pretty well aligned. Because you can, for example, then use this to create a line profile along here. Obviously, you might want to make it a little bit smaller. Or you could use it to create a proximity histogram outwards, because you can see that the center is at 0, 0 of the axis. So you could take the local axis here, 0, 0, no, 1, 0, 0, x is 1, 0, 0, and calculate all the distances to here to create a proxygram. And what we are going to do first is just to create a one-dimensional line profile, first along the entire data set, and then along the oh, thank you, Dita. Obviously the folks at Northwestern University are the pros when it comes to proximity histogram. They've created them after all. Obviously this would not be a proximity histogram, it would be a radial profile. Thank you. Thank you for that, Dita. I will just close the Manipulate ROI app, just simply because we have aligned it to the ROI. Oh, no, you know what? I'll just minimize it. Maybe we'll need it later. But if you want to realign, the ROI and you've closed the app, you can reopen the app very easily and then just say, okay, I want to work on this ROI now and move it around. And to do that, what we need to do is we need to calculate distances, right? So we need to calculate distances to create an analysis. And since we still have half an hour, I will show you how to do that so that we have a little bit more time in the ND analysis section, because this is going to be a little bit more involved. Thus it's good to have a little bit of extra time. Okay, so a 1D concentration profile along the x-axis. So you already know how to calculate concentrations for a You already know how to calculate concentrations for an entire volume. Obviously, doing that just for the ROI is fairly trivial because all you need to do is look up which atoms are in the ROI and then calculate it for the ROI. I don't think I need to separately explain that. But now we might want to calculate the 1T concentration profile along the x-axis. And the way we do that is, and now I will open up the appropriate live script. Do we have anything that oh no, it's already here. So what we do in this case is we create vectors that tell us something about the distance. And the simplest one for us is just the transformed x-axis, right? And in this case, then our analysis axis, in the ROI would be just 0, 0, 1. But we can also do it in global coordinates. If I want to do it in global coordinates, then I can go ROI.userData dot ROI x-axis, right? And then I get the axis that I wanna work with. So this would be the x-axis of the ROI in the global coordinates. Yeah. I can then create grid vectors from it. And those grid vectors, we can have them based on a constant distance, and this is what we're going to use now. And for the radial profile, what we're going to do is we're going to use a constant atom count. Yeah? Because otherwise, when we're right in the middle, we're going to have very, very few atoms within, maybe you want to have a bin count of a tenth of a nanometer, for one bin. In the middle, when we do a radial profile, in the middle we would have very few counts, or a spherical profile. In the middle we would have very few counts. And as we go outwards, we get more and more counts. So in this case, it's usually better to use constant counts. And we can do that using the bin vectors from distance function. And this gives us the bin centers and the bin edges. And in this case, a bin is just, like if we slice things up, a bin is one region of our data set where we take all of the atoms and throw them into one bin. Yeah. So maybe I'll make that a little bit smaller because we need more space here. And then maybe so that you can see that. I promise not to do this, okay? And so the distance that we want is actually the ROI.transform. So what we want is the transformed and cropped silicon. Sorry, so we will create that first. So our ROI pos then equals pos and now I need to remember what the pos in convex hull of our pos variable, and the XYZ is again our ROI.vertices. And we want all of the entries that are in there. And now it obviously calculates for a second or so, and then we have our ROI pos with about 100,000 atoms in it. And we also want to transform that, so our coordinate transformed is our ROI pos. Dot x ROI pos dot y and ROI pos dot z. And this gives us our transformed coordinates. You can see they have the same number of entries as our ROI pos. And in our ROI pos dot x equals cotrans first entry and ROI pos dot y equals the cotrans second column, and you might have guessed it, our ROI pos dot z equals our cotrans and the third entry. And don't be afraid, again, once you've got all of that typed out, you just use autocomplete as much as you can. And I can see that this may be still not optimal for you to see everything. And I will just make that a little bit wider. And just give you all of that. And now we've got the fully coordinate transformed ROI pos for all of the entries. And again, you know, that sounded like it takes 5 minutes all of the time, but once you've done that once, it just autocomplete and it goes, and it happens in seconds. And so now what we need is, we need essentially to create bins. And so we want to create bin vectors from distances. Maybe I can put them above each other. I think that might be the better way to go about this. So then you can see both things at the same time. And so now what I do is create bin centers and bin edges using bin vectors from distance. And the distance that we want is our ROI pos dot x. Okay? Because if you go here, you know, it's the red axis. It's the x-axis. It's not like there's much that's gonna be happening in that direction. And then as a bin size, what we want in this case is, I don't know, maybe 1 nanometer. And the mode that we are going to be using is, the mode that we're going to be using is not count, but just the regular mode. So I don't type anything, then we'll just sorry, maybe I need to type something. Did I do something wrong? Mode equals distance. ROI pos dot x. Thank you. Needs to be distance, not dist. Thank you, Valentin. And with that, what I get now is I get a cell array, which only has one entry. So we get to that later when we do multidimensional analysis. I could also go x and y, for example. ROI pos dot x and ROI pos dot y. And then I need two bin types, 2 bin sizes, so it would be 1 and 1 or 1 and 0.1 or whatever the hell. And then what I get, you can see I get bin centers for X and for Y. And that's why we say we have an n-dimensional binning system. So there is no difference in what you do between making a one-dimensional concentration profile, a concentration map, or a voxelization, or even a 5-dimensional map. And you can use anything that can be used as a vector. So you could, for example, look at detector XY, or you could use evaporation sequence. You could use anything that can be used as a vector. But for now, we're keeping it simple. We just use distance, and we just have one of them. Then we actually split up our data sets into sub-data sets, based on those bin edges. So I'll just call that voxelization, just like above. And that's called pos nd bin. And in that pos nd bin, we need our pos file. And in this case, we just want to have the ROI pos. Obviously, I could throw in the global pos as well. Then the distance coordinate that we want to use for that. And the distance coordinate is the ROI pos.x. And the bin edges. And the bin edges is relatively easy because we have them up there already. Bin edges. And that is it. And what we get now is we get a cell array. And what you see in the cell array is that each of the entries is essentially a POS file. So I can click on one of those and you can see, okay, I get essentially a POS file in here that I can analyze. And that's what I was talking about when I was talking about using something like deconvolution to calculate concentrations. So what you can do is apply a concentration function on each of those sub-POS variables and calculate the concentration there. And this means you're no longer dependent on saying, okay, this atom is this atom is that, but you can essentially work on the mass spectrum of each of those sub-variables. Again, we haven't implemented much of that yet because I was hoping for people like Andy to help us out a little bit here. But this is essentially what we do with the binning. And I think you can very easily see that you can do that in whatever dimension you want. So you can do that with XYZ, you can do that with evaporation sequence, you can do that with detector coordinates, you can do that with, you name it. I'm not very creative, so this is the things I came up with right now. The next thing we do is something that I already showed you yesterday, and it is creating a concentration kernel. So the concentration kernel is essentially a function that creates, that calculates the concentration for each of those sub-POS files. Yeah? So I can go into here and do the same thing that I essentially did yesterday, just now we're calling it concentration kernel. I very often abbreviate it as CK, and I think I'll do that here as well. So our concentration kernel is CK, or I kept saying you shouldn't do that, so maybe I shouldn't do that either. Let's keep it as concentration kernel. And it works on, a POS file. And what we call that is actually doesn't matter. Maybe I'll just call it X, or I just call it Dave, or whatever. It doesn't matter. It's just for the definition of the concentration kernel. Then we need all of the information that is static, that has nothing to do with the POS file itself. And that is detector efficiency, which is roughly 0.37 for our atom probe. Then the exclude list of elements that we don't want to exclude in the calculation, which in this case is only going to be hydrogen. And then a volume name, and that is going to be maybe precipitate or press or whatever. And by the way, anything that you put into here apart from the x, so the x is what we're going to be needing later. So this is going to be our POS file. Everything you put into here is actually static at the point when you created the concentration kernel. So if I have created that function already, and I go and I for example would do that on the base, calling a variable detector efficiency that f, and that is 0.37. Yeah, and then I can go and create the concentration kernel based on that variable, which I obviously can. And then I go and change that to, I bought a new atom probe and now I've got 0.82. Yeah? Then it doesn't change it for the concentration kernel, okay? So the concentration kernel, this function has the information at the time when it was created. It's something very important to remember, okay? Then I can go and take this concentration kernel and calculate the 1D concentration, and I'll just copy and paste it as it is here, and I'll just go with through the code with you. And let me just go and also copy the code for you. So now, right now, this might all seem like it's like we're taking some detours, but we're not actually taking some detours if we want to keep our system as flexible as possible. And you will see it's really helpful that you can, for example, with one and the same function set, create charge state distribution maps, create voxelizations, create concentration profiles, create a profile of the charge state ratio changing, things like that. You can all do all of that with the same system with just a few lines of code. Okay, so what we do here is we apply a concentration kernel to those bin to that bin function, and then we get a concentration 1D variable, which we'll look into later on, and we just tell it that our distance metric is in nanometers. Yeah. And you see, it doesn't take very long to calculate that. And once we have that, I can go into our cons1d variable. And it might look familiar already from yesterday. So what we have here is essentially a whole list of those concentration variables that we had yesterday with count, concentration, and variance for each of the elements. Now we obviously have a relatively small number of atoms in there, and most of them are aluminium. So very often we have no silicon, we have no whatever, because at the beginning of the precipitate there is almost no silicon, but somewhere in the middle we probably have silicon counts. Yeah. So here we have silicon counts, right? And we can then work with that, and you can see now the distance is populated. By the way, this only works for 1D profiles. For 2D profiles, we don't use the distance here. We'll do it a little bit differently. But essentially, you get a list of this entire. So this is essentially the entire 1D concentration profile, and all we need to do is plot that concentration profile. And if we want to plot that concentration profile, we can use the concentration profile plot function. And again, here we've got an exclude list. And let me just take that out from here. So in this case, obviously, what we want to plot is concentration. We could also say, okay, plot the counts for us, or plot the variances for us, or whatever the hell you want to plot. Yeah, okay, this in our concentration kernel, these are the 3 bits of information that you get. But you can think about writing a concentration kernel that gives you a lot more information per individual subvolume. And so we want to have concentrations, cons 1D. And our exclude list in this case I will just be excluding aluminium because almost all of it is aluminium, and that would be the thing that we don't want to plot. And we're going to be using the color scheme. And that now pops up with a new figure for us. And this new figure has all of the elements that we have defined in it. Yeah. Ready for you to, do all the beautiful things you can do with MATLAB. Okay, so obviously the sync is not that important for us. But what you can see is that you have the silicon, mostly on... Okay, it's a bit confusing because that's why you should go. Shouldn't it be a stairs plot? What is a stairs plot, Andy?
So you've got like this is a line plot, so you've got lines that sort of interpolate in between the points, but actually within one bin, the concentrate, like the calculated concentration is, we don't know where in that bin that point is.
Oh yeah. So you can change the plot type.
Yeah, or bars, I guess.
Yeah. The problem with so if you can go at the interpolation and actually change that to what you call a stairs plot. Yeah, that's actually perfectly possible. But anyway, so you've got all of what you need here. You can do all of the things that you're used to with your MATLAB plot. So you can go into the property inspector of the axis, for example, and change the y scale to logarithmic, or and do any of that kind of those are funky things. Right now I don't know, because usually I do all of that programmatically, so I have to look where these things are in the UI. But essentially, I've shown it to you before. You can just go and change the axis to logarithmic, or change any of the functions in there. Okay, so what I haven't shown you right now is actually a concave containment test, and we'll get to that when we get to isosurfaces, because that's where we actually mostly need the concave containment tests. But this is sort of the starting point of working with regions of interest and making some simple concentration profiles. Of course, you can also do that with a concentration map. So you can create a region of interest and do a 2D map and things like that. And this is what we will get to in the next session. But I guess we're all already very hungry. And let me just give you the last 2 lines of code. Let me just give you the last 2 lines of code. And yes, so after the lunch break, we will then continue with some more advanced analysis, where we are going to be looking into doing maybe a radial profile and doing a 2D concentration map and a voxelization possibly as well. Okay, so are there questions about the regions of interest or any? I think we've collected also some very interesting ideas. So if you have ideas of where you think, okay, maybe I could do it, maybe there would be a way to do it to do something else. Does the concentration profile plot come with an error bar function built in? I forgot if we did that. The reason why I haven't, so I believe, I'm not 100% sure whether we did that, but what I am 100% sure about is that we have included the variance, which is usually used to calculate as the counting error. That is definitely included. One of the things why I'm relatively not super happy about putting those in is one thing that I can actually show you pretty well on one of those plots is that plotting the variance doesn't, on a plot like this, doesn't make all that much sense because you can see the variance, right? So you can see that in there. The variance is the square root of the counts. Yes, it has a very defined statistical meaning. It's the square root of the counts compared to the overall count. So it's in percentage in this case. Sorry, in absolute values. But it doesn't make that much sense to plot the variance because you can see it, right? So the variance is essentially what we can see here as measurement noise or as counting noise. And as Andy has already alluded to in very big depth yesterday, this is not the actual measurement error because the measurement error is defined by a whole lot more things that we usually don't have a very good grasp on. So I personally find it a little bit misleading to put the variance in as the error bar because it is not the error, it's just the statistical shot noise, which is not necessarily an error. I think there was...
Sorry, just to find, it's an uncertainty.
It's an uncertainty, that's right. It's the variance is the uncertainty, but it's not the measurement error. Thank you, Andy. It's the variance...
I would just say, I think perhaps, so my comment would be perhaps calling it variance is slightly misleading because variance is normally applied to a population.
Well, it is the...
deviation or a variance of a population. And in this case, you don't have a population, you just have a single measurement. And you're
it's the... Sorry, yeah, it's the expectancy value of the variance.
Yeah, exactly. So there's a little nuance there.
Yeah. It's always good if people care about nuances. It's a very important thing to care about nuances.
So is it the sample or the population variance estimate that you put
there? So it's the sample variance, which means it's the sample variance is the expectancy value based on that one sample is the expectancy value of the population variance.
So then, for example, if you wanted an error bar, then you're going to need to multiply that by whatever factor you want to get whatever confidence interval you want to apply. Because you probably want something like a 95% confidence interval for your error bar.
And that is, can we maybe get a comment from Dave Reinhardt on that? Do you know what the confidence interval is? I don't know that off the top of my head, what the confidence interval is in IVAS that's used for the error bars?
The top of my head, I can't remember if it's 1 sigma or 2.
So 2 sigma would be...
That's 95%.
I thought 3 sigma is 95, or 3 sigma is already...
3 sigma is 99.
Okay, so 2 sigma would be 95. Okay, yeah. So there or thereabouts. But this is also a very good send-off that we need better concentration kernels that do a better job at estimating what the errors are. And I think adopting something like the programs from Andy London would be a very good way there, where you actually do a maximum likelihood estimation of what the actual error is. I think this would be in the future really, really helpful. For now, it's a variance, and again, I don't think so. The expectancy value of the variance, and we usually plot a confidence interval for that. And I think that's something you usually can see pretty okay in the data as it is. And so I don't think it's that helpful to plot it. Also, if you have, so now we're working at a very, very small volume, but usually we work with much larger volumes, and there they become so small that you can hardly see them anymore anyway. And it just gives the impression that that's the error, and it just isn't. Okay, but I think this was a pretty good send-off into the break. I will go for a short lunch and probably be back in about half an hour. And I'll keep the chat open so that all of you can keep chatting. And as soon as I've eaten a little bit of food, I will join into the chat as well, and hopefully be able to answer any questions that people might have.
I have a little demo of using single value decomposition to align precipitate. Can I very quickly share my screen?
Oh, yeah, absolutely.
I don't want to keep you from your lunch, but
no, but it means I need to stop the recording, and then